Psychopharmacological hypotheses of treatment-resistant schizophrenia. Schizophrenia directly affects over 21 million people globally. Up to 1 in 3 patients with schizophrenia meet the criteria for TRS. Treatment-resistant schizophrenia, or TRS, is broadly defined in clinical guidelines as a lack of response in target schizophrenia symptoms following treatment with at least 2 antipsychotic treatments of adequate dose, duration, and adherence. TRS has a severe clinical and economic impact on patients, carers, families, and society as a whole. Research on TRS has generated several hypotheses for explaining the underlying pathophysiology. The following video presents one hypothesis for explaining TRS with the aim to develop new treatments. Here, the focus will be on the corticostriatal thalamic circuitry, containing specific interlinked brain areas thought to be involved in the pathophysiology of schizophrenia. These areas include the striatum, the globus pallidus externus, the subthalamic nucleus, the substantia nigra, the thalamus, and the cortex. Each region within this circuitry is connected to another via inhibitory GABAergic or excitatory glutamatergic pathways. The striatum is linked to the substantia nigra via 2 distinct downstream pathways. The direct pathway, controlled by stimulatory dopamine D1 receptor-expressing neurons, and the indirect pathway, controlled by inhibitory dopamine D2 receptor-expressing neurons. The structures within the corticostriatal thalamic circuitry are connected by excitatory glutamatergic signals and inhibitory GABAergic signals. The direct and indirect pathways of the corticostriatal thalamic circuitry. Dopamine in the striatum regulates the activity in the direct and indirect striatal pathways. The changes in activity via both pathways lead to modifications in the regulation of the thalamocortical pathway. In patients with schizophrenia, dopamine levels are increased in the striatum. Excessive dopamine projecting from the VTA overactivates the D1 receptors of the direct pathway and D2 receptors of the indirect pathway, leading to a dysregulation of the thalamocortical circuitry, including inhibition of the subthalamic nucleus, disinhibition of the thalamus, and overactivation of the cortex. This is believed to contribute to the positive symptoms of schizophrenia. Schizophrenia may be treated with D2 receptor-preferring antagonists or partial agonists. Although many antipsychotics modulate a range of receptors, they preferentially target D2 over D1 receptors, exerting antagonism or partial agonism properties. D2 receptor antagonists and partial agonists prevent the overstimulation of the D2 receptors controlling the indirect pathway. And in approximately 2/3 of patients, this leads to an alleviation of positive symptoms of schizophrenia, such as hallucinations and delusions. In these patients, D2 receptor-preferring antagonists or partial agonists appears to be sufficient for a clinically relevant improvement in positive symptoms, whereas D1 receptor antagonists alone are ineffective. Up to 1 in 3 patients do not benefit from antipsychotics preferentially targeting the D2 receptor. Patients with TRS have persistent, moderate to severe positive symptoms, despite treatment with a D2 receptor-preferring antagonist or partial agonist. In patients with TRS, a combination of blockade of the D1 direct pathway and the D2 indirect pathway may improve symptoms. It has been shown in animal models that the combination of D1 and D2 receptor blockade works in synergy. Based on this evidence, the hypothesis emerges that in patients with TRS, a combination of blockade of the D1 direct pathway and the D2 indirect pathway should be investigated as a potential target for the treatment of TRS.